So this is a different lab, very different type of lab. It's called the phase diagram of a three-component system, and it investigates the mutual solubility of three liquids: water, butanol, and acetic acid. So the first part of this presentation is really just a PowerPoint where I'm going to put audio on it and use the video to show you the slides. And then after that, I'll go right into actually doing the lab and showing you everything, all the different parts and how they come together to be able to calculate this phase diagram. This lab is actually about the mutual solubility or lack of solubility of the three liquids: water, 1-butanol, and acetic acid. And as you probably already know, water and butanol do not mutually dissolve. We say they don't mix. When you mix them up, they will separate into two layers. But water and acetic acid, as you know, do mix. In other words, they mutually dissolve. So what this lab is about is figuring out what compositions of water, butanol, and acetic acid lead to a mixture that separates, that would be two phases, and which would lead to one phase. So what I do on this slide is pose the question: when liquids are mixed, what determines whether they will dissolve in each other? And what determines that is the free energy of mixing. Okay, so as with reactions, if the delta G for mixing is negative, the substances will mix spontaneously, just like if delta G for a reaction is negative, they'll react spontaneously. And when I say mixing, I want to reiterate that I really mean dissolving here. Okay, so if they dissolve in each other, if they mix, then you'll get one layer, like ethanol and water. It's mutually soluble in all proportions. If they don't mix, don't dissolve in each other, that's what I mean there, you'll get two layers or two phases. So that's the beginning. That's where we start with this lab. So as with any delta G for a reaction, the delta G from mixing also consists of two terms. There's the enthalpy contribution, delta H mixing, and then there's the entropy contribution, minus T delta S of mixing, okay? And the entropy contribution, entropy being just really disorder, which we'll learn a lot more about later in the term, mixing generally increases disorder. So the delta S, the entropy change for going from not mixed to mixed, going from not dissolved in each other to dissolved, is generally positive. There are exceptions to this, the hydrophobic effect, for example. But because delta S mixing is almost always positive, the minus T delta S mixing contribution to delta G mix is generally negative, and that would promote mixing, right? So we say that entropy favors mixing, and I often refer to this as nature's tendency to mix things up, okay? So that's the entropy portion. The enthalpy contribution can be positive, negative, or zero. Usually it's either positive or near zero. And it depends on the specific interactions between the molecules involved. So if you're mixing two molecules, A and B, and if the attractions of A and B for each other are not as strong as between A and B, then what happens is it requires more energy to pull those AA and BBs apart than you get released when you put them together, and it makes the overall mixing process positive, the delta H be positive. However, if the attractions of A and B are about as strong as between AA and B, and I'm talking about these intermolecular forces, then the delta H of mixing will be close to zero. In other words, the amount of energy that's required to pull AA and BB apart, right, to break those intermolecular forces, would be about the same as the energy released when you bring A and B together, and that would make the delta H mixing be near zero. Well, if the delta H mixing is near zero, then entropy is going to favor mixing, and that will make the delta G negative. If the delta H mixing is negative, which doesn't happen very often, then the enthalpy favors mixing, and the entropy always favors mixing, so you will end up with a negative delta G. It's when delta H mixing is positive that things are a little interesting, right? Because then it depends on the relative magnitudes of those two terms. And so if delta H mixing is a greater magnitude than the T delta S term, then if delta H is positive, then it makes delta G positive, okay? And if it's positive enough, they will not mutually dissolve. So to start off, I need to talk about the graph paper that's used to make a phase diagram, because a lot of understanding this presentation is understanding what this triangular graph means, okay? So we have what's called a three-component phase diagram that we're trying to draw. And each point on this graph, this is like the empty paper. This has no information on it, but you need to understand the graph paper anyway. So each point on the graph represents a composition. Each point represents the percent by mass of each of the components, A, B, and C, in the mixture. So what we're going to do in this lab is try to figure out which portions of this triangular graph, in other words, which compositions end up giving you one phase and which end up giving you two phases. So I'll try to explain this diagram very thoroughly on the next slides. So on this first of the set of slides explaining the meaning of this triangular graph, I show you that each of the vertices, each of the three vertices represents 100% of one of the compounds, right? So we have 100% acetic acid, A, 100% butanol, and 100% water. Okay, so A, B, and C are acetic acid, butanol, and water. So when you're at a corner, that means you have only one of the components present. All right, so now it starts to get a little more interesting. All right, so the lines that connect each of that connect two adjacent vertices represent mixtures of just those two components. So you can see the red line represents only mixtures of butanol and acetic acid. The blue line refers to compositions that are just mixtures of two of the butanol component and the water component, and the green line refers to mixtures of acetic acid and water only. All right, so now this diagram starts talking about the middle of this triangular graph. So for example, let's take that green point right in the middle, okay? So that point represents a certain composition of A, B, and C. So how do you figure out what its composition is? Well, what I always do is I start with a vertex, like the 100% A on top. So if that point is 100% A, right at the tip of that, the top of that triangle, I go down to the line that's opposite it, okay? That line that connects B and C. Okay, the line connecting B and C has 0% A. And then I start counting up 10% at a time, so that the next line is 10% A, and the next is 20, 30. And then you see the red line that's on 40% A. And so that green point is made up of 40% acetic acid. That's what that composition represents. But of course, it's got to have the others in it as well. So how do I figure out the percent B? Well, I start at the 100% B vertex, and I go to the line that's opposite that vertex. And that line is 0% B. And then I start counting up 10, 20, 30, 40% B. That's how you do it. And then the remainder is C, okay? And then you could see that if you go to the vertex opposite the 100% C, the line opposite it, that's 0% C, that you only need to get to 20% to get to the red line, and the intersection of those three lines is that data point, is that composition, 40% A, 40% B, and 20% C. So every single point on that triangular graph represents an individual composition, an individual percent of A, B, and C. Unless something is drawn on that phase diagram, there's absolutely no information. That's like just like showing you a blank piece of graph paper. What we need to do is identify which areas on that diagram represent mixtures that give you one phase that are complete, where they're completely mutually soluble, and which parts of that diagram, which compositions lead to where you do not have one phase but you have two. And that's what we're going to try to do in this lab, is figure out where the boundary is between the one phase and the two phase regions on this phase diagram. The diagram shown here is kind of a hypothetical phase diagram. I mean, it looks something like this, the real phase diagram, but you can't get any real information out of this. It's not correct. But it basically does identify a one phase region and a two phase region. And all compositions under that red curve there would lead to two phases. And all the other compositions would lead to a solution or one phase. Okay? And I'm just going to tell you something from the start, and that is, if you have a mixture that's like 50-50 butanol and water, so sort of halfway across that bottom line, you're right squarely in the middle of the two-phase region. And if you add acetic acid to that, so you're basically going up towards the 100% A vertex, what's going to happen eventually is that you will not have two phases. You will mutually dissolve those three liquids. You will enter the one phase region. And that's one of our jobs, is trying to figure out where that boundary line is. That's the main job, actually, of the lab tonight. So this slide illustrates parts 1 and 2 of the lab. And basically, these two parts are really it's one part, but there's two different proportions of water and butanol. And what we're doing here is we're investigating the mutual solubility or lack of solubility between just butanol and water. Okay, so what's done is you add water, 20 mils, into a graduated cylinder. Then you add butanol, 40 mils. And you basically stir this up very rapidly with a stir bar, and then you do the almost the same thing, except 40 mils of water and 20 mils of butanol. And basically what you do is you measure the volumes of water and butanol before you mix them, right? And then after you mix them, you let the layers settle, and you see if those volumes have changed at all, okay? And you copy down where the layer is seen, where the middle layer, the middle line is seen, and where the top is. So all of those numbers get recorded, all right? But let's think about what's present at this point in this mixture, okay? After you mix it and you let it settle, first of all, water is more dense, so it's going to be on the bottom. So the top layer is mostly butanol because not much water dissolves, but a little bit of water does dissolve in butanol. So there's a little water in that top layer. And in fact, because you've stirred and stirred and stirred this, that top layer is a saturated solution of water in butanol. And the bottom layer has a little bit of butanol dissolved. So it is a saturated solution of butanol and water. And the other graduated cylinder, the top layer, is also a saturated solution of water and butanol. So it's also mostly butanol and has a little bit of water dissolved in it. And the bottom layer is a saturated solution of butanol and water. So the two bottom layers actually both have the same composition. They are both saturated solutions of butanol and water, and the top layers are saturated solutions of water and butanol. Okay, so it turns out that the data that you take when you do those parts 1 and 2 for those different volumes is enough to figure out what the composition of a saturated solution of butanol in water and a saturated solution of water in butanol is. So basically you'll be determining, like it says in the first bullet, the concentrations of butanol and of water in those saturated solutions. And what this amounts to is determining the bottom 2 points in the phase diagram. Okay, so the point on the left represents a saturated solution of water in butanol. It is mostly butanol, and you could see that it's on the butanol-rich side. It's on the 100% B side. Okay, so if you get your results and you find you have a composition of one of those layers that was, a much greater percentage butanol than water, you know that that point belongs over on the B end of the curve. Okay, and then the other one on the C end of the curve was for the bottom layer that was the saturated solution of butanol and water. So it's a little bit of a long story on how you can use that data to get those two compositions, but I'll try to go through it pretty swiftly on the next couple of slides. So how do we get those two compositions? Well, I already pointed out to you, and it's very important, that the upper layers have the same concentration of water and of butanol, and that concentration is that of the saturated solution. And the same is true of the lower layer. That's also the same for both trials. So both bottom layers have the same composition. So the top layer for both is a saturated solution of water and butanol, and the bottom is a saturated solution of butanol and water. Okay, so if we call the concentration of water in the upper layer CWU, okay, that's the same for both trials since they're both saturated solutions. And the same, of course, is true for the concentration of butanol in the upper layer, CBU. And also the same is true for the lower layers for water and butanol. So the concentration of water in the lower, CWL, and CBL, the concentration of butanol in the lower, are also the same for both graduated cylinders. And this allows us, this is really great, it allows us to calculate what these concentrations are from the data by solving simultaneous equations, which you're not going to have to do. I have a nice Excel spreadsheet that does it all for you, but I am going to go through how it's done, okay? And once again, these are the concentrations that are the compositions of these represent the compositions of the two red points on that triangular graph on the bottom. And here's my absolutely favorite slide of all, showing you all the equations that are used to solve for these different concentrations. Well, not really, but I will go through this with you pretty quickly. So basically what's done is you take those volumes of water that were used for each trial, and you could convert them to masses, okay, using the density. And you could do the same for butanol. So you end up with the mass of water in the first trial and the mass of water in the second trial. And those can be calculated quite easily. And then the volume of butanol for each trial can also be converted to a mass using butanol's density. And so you get the mass of butanol in the first and the second trial. And then there are the volume of the entire lower layer in trial 1, VL1, and in trial 2, VL2, and the volume of the upper layer in trial 1 and trial 2. So what's then done is these are all put together in what we call these conservation of mass equations, which basically says that the total mass of water in trial 1 has to equal the sum of the mass of water in the lower layer for trial 1 and the mass of water in the upper layer. And remember, I said those concentrations were in grams per volume, gram per liter. So that's CWL. When you multiply that by the volume of the lower layer in trial 1, you'll get the mass of water in the lower layer. And then if you take the concentration of water in the upper layer and you multiply it by the volume of the upper layer in that trial, that will be the mass of water in the upper layer. So you add those two together and you get MW1. And the very same thing works for the mass of water in trial 2. And similarly, you can get two other equations for the mass of butanol in the two trials. Now, if you look at the two equations that are written here, you see that the only unknowns are CWL and CWU, okay? That all those other things are known. And so what you end up with when you do the butanol equations as well is that you have 4 unknowns and 4 equations. And they can be solved for these concentrations of water in the lower layer, upper layer, and butanol in the lower layer and upper layer. So you're going to get those saturated solution concentrations. Now, you don't have to solve those simultaneous equations. I've used Excel to do it, and I have a spreadsheet for it. So basically, you will input the numbers that you get for trial 1 and trial 2. You'll input the volumes before and after mixing, and then the Excel spreadsheet will instantly calculate what the compositions of those bottom 2 points on the phase diagram are. All right, so that's great. That's 2 points on the phase diagram. But how do you get the rest of it? You know, the real meat of this phase diagram curve is the red curve, okay? That the boundary between the 2 phase region, which is below the red curve, and the 1 phase region, which is above it. All right, so let's take and look at number 1 here, okay? So make a mixture of just butanol and water in the 2 phase region. So look at that nice fat blue point on the bottom of the phase diagram. That's where you're going to start, mixing a significant amount of butanol and water together so that it would be 2 layers. And then what you're going to do, and basically you're going to be stirring this mixture constantly. Now, when you have butanol and water and you're in the 2 phase region and you're stirring the mixture, it's going to be quite cloudy, okay? And so then what you're going to do is you're going to add acetic acid. So when you're adding acetic acid, you're increasing the concentration of A. So the direction for a greater concentration of A would be to be moving up this diagram. So that little blue arrow I draw coming out of that blue point is what happens to the composition as you add acetic acid. And at some point, the acetic acid addition is going to cause the butanol and water and acetic acid to all become mutually soluble. So instead of it being 2 layers, it'll be 1 layer. So as you're mixing this solution, well, this is not a solution, as you're mixing this mixture and it's cloudy and you're dripping really by drops acetic acid from a burette into this stirred up water butanol mixture, at some point, this mixture goes from cloudy to clear. And that is what we call the turbid point. And when you get to that point where the mixture clears up, then you stop the burette and you look at the volume of acetic acid that you have added, okay? And you'll be able to figure out what the composition of butanol, water, and acetic acid is when you get to that turbid point. And that would give you one of those boundary points along that red curve. But of course, you can't make this diagram with 1 point. So what you then do is you will add water to your mixture. And that will bring you back. That's the dotted line. It'll bring you back because that's the dotted line goes in a direction of what would happen when you add water. Okay, you'll go towards the 100% C vertex. Then you'll start to add acetic acid again, and it'll be cloudy, and then it'll clear up at the turbid point, that tip of that blue arrow. Then you'll do the dotted line again, add more water, add more acetic acid, add more water, add more acetic acid, until you get to the turbid point. And all those turbid points will map out the boundary of the 1 and the 2 phase region. And I think that's pretty clever. So when I talk about composition in this lab, there are really 2 different types of composition that I've referred to. First of all, we have the overall composition of a mixture. So, if you mix butanol, water, and acetic acid together, mix it up, it has a certain percent water by mass, a certain percent butanol, and a certain percent of acetic acid. If you then let this mixture separate into 2 phases, now you can think about the composition of each phase, okay? And we've actually done this once, right? Parts 1 and 2, when we had those 2 graduated cylinders, we mixed 20 milliliters of butanol with 40 milliliters of water. And then we mixed 40 milliliters of water with 20 milliliters of butanol. Each of those 2 mixtures for trial 1 and trial 2 had very different overall compositions, very different percentages by mass of A, B, and C. However, they had something very big in common, and that is that they had the same compositions in their upper layers and their same compositions in their lower layers because they were both saturated solutions. Okay, so that part actually did address the composition of each phase. Okay, and that red point on the left represented the composition of the phase that was the butanol-rich saturated solution. In other words, a saturated solution of water and butanol, and the red point on the right represented the saturated solution of butanol in water. So there's a feature on this type of phase diagram, which is called a tie line. And there's actually a theorem that can be proven, which we're not going to prove, that says that there is a line that connects the composition of each phase to the overall composition. All right, that's a little bit esoteric, but let's look at the bottom line of this phase diagram. Okay, so on the bottom of this phase diagram, I have 4 black points sitting on the bottom line. Those are 4 very different overall compositions of a mixture of butanol and water, and all 4 of them lead to 2 phases. Okay? However, if you stir up the butanol in water, regardless of what that overall composition is, you always end up with the same concentration for the upper layer and the same concentration for the lower layer because they are saturated solutions. The top one of water and butanol, the bottom one of butanol and water. So all of the points on the blue line on the bottom of this graph, all of those, if you can imagine, they're all really black points, right? They're all overall composition points. They all have the same composition of each phase when you separate them. And that line, that blue line, is called a tie line. So tie lines are drawn that link the point for overall composition, which would be in the middle of that line or somewhere in, not on the ends, that links that point to the composition of each phase. And so we actually have already found, we already found one tie line with basically the bottom line that connects the 2 red points for the saturated solution. Well, it turns out that every point in the 2-phase region on a phase diagram, every overall composition has a line that connects the boundary on each side to that black point. So if you look, there's one line shown there with a black point, okay, and it's got a percentage A. It's not on the bottom any longer, and it has 2 red points, and the red points there represent the composition of what I call the butanol-rich layer and the water-rich layer. Okay, the water-rich layer would be on the right, that right red point, and the butanol-rich would be on the left. And I can no longer say saturated solution because now it's got 3 things in it because it's got some acetic acid in it. So every one of those, every black point in that entire 2-phase region has such a line that connects the compositions of each of the 2 phases. And like I said, it can be proven that these are lines, but we're not doing that. Well, there's an infinite number of these tie lines, okay? We're just going to find one, all right? We already found the bottom one, but that's sort of a trivial case because it doesn't have any acetic acid. So what we're going to do is make a mixture of butanol and water and acetic acid that is squarely in that 2-phase region. And then we are going to mix it up, okay? And then we're going to separate the layers. And then we're going to figure out the amount of acetic acid in each of those layers. And that's going to give us those 2 red points. So that's the last thing that we're going to be doing. So you might ask, how are we going to do this? How are we going to figure out where to put those 2 red dots for that tie line in the center of the 2-phase region? And what we're going to do is we're going to separate the 2 layers, as I said, and then we're going to take the bottom layer and we're going to titrate it with sodium hydroxide and figure out the moles and then the mass of acetic acid that is in that bottom layer, okay? And we know that we will have pipetted a certain volume of acetic acid, which we can convert to grams. And then we can subtract the number of grams in the bottom layer from the total grams, and that will give us the grams of acetic acid in the upper layer. We will use that and the total mass of the layer to find the percent acetic acid in the bottom layer and in the top layer. And you might ask, well, how are we going to figure out where the red points are if we don't know the compositions of the butanol and the water? But actually we do, because we have already mapped out that boundary line. So all we need to do, let's say for the upper layer, we've got a certain percent by mass of acetic acid. All we need to do is go up to that percentage, right? Up to that percent A, and see where that intersects the two-phase region boundary, and that's where we put the point. And we do the same thing for the upper layer, the butanol-rich layer. We find that percentage, we go up from the bottom to that percent of acetic acid, and we see where it hits the boundary, and that's what we will put on our phase diagram and connect it. And actually, we could even verify that it's on a line. We could see if the overall composition is actually on the same line when we draw it on the phase diagram. And this last slide just shows some of the equipment that we're going to use to find that tie line. That's part 4. It just shows that you will make a mixture of 25 mils each of butanol and water, and you'll add 3 mils of acetic acid by pipette, be in the two-phase region. Then we'll mix them together and let the layers form and separate with the SEP funnel that's shown there at the right. I think on top, that beaker, Erlenmeyer should be showing a cloudy mixture. I think ours came out better than that when we actually did it. So then you're going to separate the layers, weigh each layer, and titrate the water layer using phenolphthalein as an indicator. Okay, and then find out the percent acetic acid in that lower layer, which allows you to figure out the total mass in each of the layers and convert those to percents acetic acid for each of the layers. And that's basically it. All right, so we're ready to determine the bottom 2 points in the phase diagram. So this is the setup for parts 1 and 2. We also call them trials 1 and 2. I don't know why we use both those terms. I probably should change it in the lab handout, but what we're going to be doing here is investigating the bottom line of the phase diagram, which is the water and butanol mixtures only. Okay, so we're not adding any acetic acid yet to this part. And so what I have here are 2 graduated cylinders, 200 ml graduated cylinders, and they have ground glass stoppers. And what I'm going to do is, for the first trial, first part, I'm going to put 20 milliliters of water by pipette, but then I'm going to read it on the graduated cylinder. Then I'm going to add a stir bar, and I'm going to read the volume on the cylinder after I add the stir bar. And then I'm going to pipette 40 milliliters of butanol. And then over here in trial 2, it's very similar, except I'll add 40 mils of water, and then the stir bar, and then 20 milliliters of butanol. And then what I'm going to do is I'm going to put the stir bar in each one of these graduated cylinders. So I'm going to put the stir bar in when I'm finished putting those amounts of the liquids in. I'm going to stopper it, and I'm going to stir it, okay? And when it stirs, you should see it very cloudy throughout the entire graduated cylinder, and make sure it gets good and stirred, good and mixed up. And the same thing for the other one. And then what we're going to do is record where that dividing line is between the 2 layers and where the top volume is. And then we're going to input those volumes into an Excel spreadsheet that allows calculation of the concentration of water in the upper layer and the concentration of butanol in the upper layer, and then the concentrations of those also in the lower layer. And the compositions of the top layers and the bottom layers, as was explained early in this video, are the same, because the top layer is a saturated solution of water and butanol, and the bottom layer is a saturated solution of butanol and water. Okay, so I'm going to do that pipetting, and I'll get back to you. All right, so I just got through pipetting 20 milliliters of water into this graduated cylinder, and when I measure its volume, I find that it's 20.2 milliliters. So I'm going to record that on my data. And now I have to put a stir bar in there. I'm going to dump it right in. Not very graceful. And now I have to actually measure the what the volume is again, which I'm going to do away from the camera. I would say it's 21.3. It's hard to tell here, but that's what I read. And in this other graduated cylinder, I pipetted 40 milliliters of water. And when I read this one close up, I thought that it was just about at 40.0 milliliters of water. And then now I'm going to dump the stir bar in there as well. And check the volume again. And probably can't see the volume pretty well here. I just can't do it at the same time. So let's see what I think it is. 41.2. 41.2 with the stir bar. And now I have to add 40 milliliters of butanol for the first trial. So I'll pipette 20 mils twice, and then 20 mils of butanol for the second trial. I'll be back. All right, so I did exactly what I said I was going to do. I added 40 milliliters of butanol to the 20 mils of water in trial 1. And then I added 20 milliliters of butanol to the 40 milliliters of water in trial 2. And I didn't mix it up at all. Now I have to try to measure where the meniscus is. And it looks like it's well above 60, because I did add the stir bar. I would say it's 61.7. 61.7 is the total volume now after adding the butanol. 61.7 milliliters. Let's go over here. So I'm going to do the same for this one. This looks like 61.4 milliliters. Okay. When you look straight on it, it's 61.4. All right. Now what I have to do is mix it like crazy. So let's see what happens here. I have to really play with this to get it to work. I would really like the entire thing to be cloudy, just like that. Great. Let's try this one. Let's put this in the middle. Oh boy, this one sounds like a train coming down. Making a lot of noise. And it does seem to be cloudy all the way through. So what I'm going to do is just let this mix for like 10 minutes. And we'll come back after and take our final readings. Okay, so this is trial 1. And the bottom layer for trial 1, just about right at 15. You can see, I'm going to call it 15.0. And the top layer, it's really almost impossible to do this in real, to really show you this. It looks like it's like 61 point, maybe 0.3. So 61.3 and 15.0 total volume. Okay. All right, now I'm going to go and get the same type of data from trial 2. All right. That bottom layer is a little higher up, so it's a little easier to see. But I have to get my eye right at that level. It's hard with the camera, honestly. I feel like an idiot. Looks like it's between 41 and 42. Okay, but I'm going to try to get it better. Actually, it looks like it's just about like 41.8. Now I have to get the total volume. Looks like it's a little above 60, it should be. Okay. 62 maybe. So it looks like it's between 61 and 62. I'm going to try to get it better. I say it's 61.2. 61.2. Okay, so you could see that the volumes didn't change much after mixing. Went from 61.7 to 61.3, and this one went from 61.4 to 61.2. But the bottom layer, certainly that dividing line here, it was 21.3, now it's 15. Okay, here it was 41.2, now it's 41.8. Okay, so that's all the data we need for parts 1 and 2. So this is the data that I collected for parts 1 and 2 of the lab. And this is the data that's going to be inputted into an Excel spreadsheet that I have posted on Blackboard. And the output of that spreadsheet will be the concentrations of water and butanol in the upper layer and water and butanol in the lower layer. Okay. So now we're up to the longest part of this lab, which is part 3, which is determining the boundary between the 1-phase and the 2-phase region on that phase diagram. And here is where we'll be finding what I've called the turbid points, points where we just add enough acetic acid for the mixture of butanol and water to go from cloudy to clear. We're in part 3 now, and I'm going to pipette 20 milliliters of butanol into here, and then this is water. I'm going to pipette 5 milliliters of water into the same flask. Then I'm going to prepare this burette by putting concentrated, glacial acetic acid in it, and I'm going to get ready to drip the acetic acid into this water butanol mixture while it's stirring. So that's the basic idea. Everything is all clean and dry. milliliters. Butanol doesn't smell very pretty, I'll tell you. Smells pretty foul. So I'm glad I'm doing this in the nice hood. That's all the butanol I'm going to need for a while. If there's a drop hanging, you just leave it. Okay, that's the butanol. And now I'm going to pipette 5 milliliters of water. Let's see if I can find the right pipette. Here we go. They're all labeled. So what I've just done is I've carefully poured some glacial acetic acid into this little beaker here, and now I'm going to fill the burette with it. All right, that meniscus is on the zero point. Let me see. Oh, that's pretty good. Right, 0.00 will be my initial volume. I'm going to get a piece of black cloth. I'm going to put right here. I'm going to get a stir bar. Right here. Stir this up. And what I'm hoping is that you can see that it's cloudy. This tripod is not the greatest. All right. I think you can see it's cloudy. Let me turn the lights out because sometimes that's helpful. Looks pretty cloudy. Right, sometimes we even shine a light on it. Let's see if that helps. Like a spotlight. I'm going to drip some acetic acid into that. It's going at a very slow pace, those drips, I think. Yeah, so slow it's practically not happening at all. Maybe that's a good thing. And so what we're looking for is for this cloudiness to become clear. That's the turbid point. And I've heard that the first one for this experiment is a little difficult to see. So we'll see. It still looks cloudy to me. Of course, not very much has dripped in. Drop. I don't even know if you can see it. Another drop. drop, drop, drop. I'll put 5 of them and I'll stop it. That is still cloudy. Let's see where we are. By the way, turn the light on. Oh wow, you can see with the light on. So, just want to see about where I am. Yeah, I haven't even gotten, I don't think, to a milliliter yet. But I don't think I have to put much more than a milliliter for this first one. So let's be careful. Get my eyes acclimated again. That's enough. Clear from the top, but cloudy from the side, so I would like it to look clear on all sides. So I'm going to turn the light on, put another few drops in. Alright. Light off again. I know this is hard to see. Let's see where I am. I don't even think I'm up to a milliliter yet. Pretty sure it's supposed to be over a milliliter. Yeah, I'm gonna keep going. Well, I don't have to have the light off when I'm putting the drops in. So. 1, 2, 3, 4, 5, about. It still looks kind of cloudy to me. Take that reading just to have it, and then see if it really is done. So that looks like it's 0.93 milliliters. I'll just write that down. But I'm going to add a few more drops because I still think it looks a little cloudy. Of course, then I went nuts and added like way more than just a few drops. Still looks cloudy to me. Oh, I think it looks clear now. Oh my God, it really is clear now. Very cool. I haven't done this experiment myself in years, so, but that was pretty, I think, pretty clear. Okay, so this is 1.1, let's call it 1.14 milliliters. So our first turbid point just happened, and now we're going to get a turbid again. How? I'm going to add 5 milliliters. Sorry, I'm going to add 5 more. That's a really shoddy construction. I'm going to add 5 more milliliters of water, and that's going to put us back in the two-phase region. Right in here. I lost a drop, but nobody's perfect. And you could see it clouding right up again. Okay. So now I know that I was at 1.14. That's my initial volume for this one. Just putting drops in. Alright, so I'm going to put in a little bit. See, put the light out. It's still dark. I mean, it's still cloudy. Put some more in. I don't know if you need that light off because I can see very clearly that it's cloudy right now. Still looking cloudy. Still looks cloudy, very clearly cloudy. Still cloudy. It still looks cloudy. That's 12 drops now. That's 10 more drops. Still looks cloudy. Turn the light out. Definitely cloudy. Still looks cloudy. Still cloudy. If I could just wait for it to clear up, just add the drops, and at some point see a big change. I'm not sure. Looks cloudy. I'm not sure. I think it cleared up. Yep, look at that. I may have added a few extra drops, I'm not quite sure. But that looks very clear right now. Boy, it's really cool. And now I am at, oh boy, I'd say 3.90 milliliters. Guess what? I add another 5 milliliters of water, and I'm going to get back in the turbid range, back in the two-phase region. God, it's so clear now. 5 mils. I'm going to cloud right up. You know, I like this experiment more than I thought I was going to like it. It's really cool to see. Cloudy. All right. And in the dark, cloudy. All right, so now 3.90 is my initial volume. And I'm recording this all on a data sheet, which I'd show you, except the camera's in a very precarious, I like where it is, so I'm just gonna leave it right there. So we just add some drops. All right, that was 10 drops. Let it mix a little. Drops. Still cloudy. I don't know if the spotlight really does anything. I don't think it matters. I'm not going to bother with it. I'm not even bothering turning the lights out. Got 7 more drops. Still looks quite cloudy. Another 7 drops. Good. 3 or 4 drops. Cloudy. Oops, that's a whole lot of drops. Still cloudy. Good. Dodged a bullet there. Tighten this a little. Too much. Another bunch of drops. But I actually haven't even added a milliliter since the last reading. Try to be careful because I'm going too fast. There we go. Still looks cloudy. Probably move this out of the background. Should have done that a while ago. Oh well. Just 1 drop. Drops, still cloudy. I have a feeling it's going to happen soon. I don't know, just have a feeling. So now I'm going really slow. Like almost not going at all. Drop. 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 Oh, look at this. It's clearing. Maybe I jumped. Maybe not quite yet, but I think it's really close. I got a pretty good reading that time. Pretty good. Go over the end point or the turbid point. It's 5.41 milliliters. Right. And now I add another 5 mils. So let's see, this is, I added 5 initially, then I added 5 more, then I added 5 more, and then this is now the 4th addition. including the initial one. Watch it cloud up. Look at that. It clouds right up. So it's clear that the acetic acid, adding it, helps butanol and water mutually dissolve. Right? Quick drops. Let it stir. Another. Just gonna let it go slow. One. So it's just dripping very slowly, continuously. Gotta go a little faster. Okay, let it stir. Drops. Drop. It's going like that. I'm just staring at it. It's getting close. I think it's getting close. Look at that. Look at that. Cleared right up. Wow. It's really cool. I guess that's why I'm a chemistry geek. So this is 6.42. It's just about a milliliter. I'm going to add 5 milliliters again. And it clouds right up. Okay. Dropping in very slowly but continuously until I get bored and I want to make it a little faster. Let's stir. How to get a good stir. Ooh, look at that. Just cleared right up. Almost. Is it really? Huh, I think it's the turbid point. Not sure. Maybe just a little bit quite. Almost. One more drop. I think that's it. Yeah, so look how clear it is. You can see it from here. It's just clear, clear from the side, clear from the top. It's not cloudy, so that's, yeah, there you can see how clear it is, I think. Okay, so at this point the camera went blank. I don't know why that happened, but that didn't stop me from taking a reading of 7.30 for the milliliters of acetic acid. And so at this point, the mixture contains 25 mils of butanol, 20 milliliters of butanol, that hasn't changed, 25 milliliters of water, and 7.30 milliliters of acetic acid. And also, while the camera was blank, I didn't realize it, so I added the next portion of water, which is another 5 milliliter portion, which brings the total volume of water now to 30 milliliters. And of course, we still have 20 milliliters of butanol in there as well. And then I just started adding acetic acid to get to the turbid point once again. And where this video resumes, I am almost at the turbid point for that 6th edition, that 30 milliliters of water. I'm just almost ready to read the burette volume of the acetic acid. Wait, I think I maybe need one more drop here. One more. That's pretty clear, so I'm going to get the reading. Okay. It's like 8.03 milliliters. All right, so now we're going to switch to adding 10 milliliter portions of water instead of 5. And now I'm going to add 10 milliliters of water. And I'm going to do that, oh my, 8 times to get all this data. So I'm not sure I'm going to actually make you watch all this, but I'm going to get a 10 ml pipette for the water. Okay. Watch it cloud up. I saw it cloud right up. I've just added my first 10 milliliter portion of water. Acetic acid now. A bunch at the beginning. Another bunch. It's quite a big bunch, but it's still cloudy. Because I added 10 mils of water this time, not 5. It was getting less and less each time. I was adding less and less acetic acid, but now I added a whole lot more water, so I'm going to have to add more acetic acid. It's 5 more drops. 5 drops. It's looking like it's going to be soon. I don't know. Maybe not that soon. It's still pretty cloudy. Although I think it would go from cloudy all at once to clear. I don't, but it seems like it's sort of happening more gradually than I thought. It still looks pretty cloudy. Just adding continuously, but slowly. Doesn't look like I'm there yet. But now I am, if not there, I am very close. It's just cleared up a lot, but I still see a certain little bit of cloudiness, which I don't really understand. It should either be cloudy or clear, but okay, there's one more drop. Just one more drop. It's been pretty clear, but it's got a little. There's one more drop. I'm going to call that it. That's the turbid point for this one. I don't know, maybe one more drop. Of course, I added 6 drops, but them's the breaks. Okay, so that's definitely clear. Let's see, that's 9.43. Right now I add another 10. Look at that bubbling. That seems to happen near this turbid point. I don't know. All right, another 10 mils of water. Bubbles kind of go away. It gets cloudy. Very interesting. Right, there's 10 more mils of water. I'm very close to the edge. All right, now I'm going to start adding acetic acid again. Bunch of drops. Oh, just cleared up. All right, I'm going to take that volume. .12 milliliters. Now I have a little bit of a confession to make. It was getting kind of late in the day when I was doing this experiment. I guess that's my excuse. But after I added the water, it was supposed to be 10 milliliters, but I had a 5 milliliter pipette under that hood as well. And I saw that the pipette I had used, at least I thought I had used, was the 5 milliliter pipette, not the 10. And so that was what I thought at the time. And I wondered if I could prove that I had done that. So when I finished making the video, I went back and I timed how long it took for 5 milliliters of water to flow into the flask. And it took about 10 seconds. And then I timed how long it took a 10 milliliter sample of water to flow into the flask. And that was about 15 seconds. So when I looked at the video for what was supposed to be the second edition of 10 mils, I timed the flow of water and it was only 10 seconds, which corroborated my thinking that I had only added the 5 mils. So to conclude, I only added 5 milliliters for what was supposed to be the second addition of 10, but this doesn't matter as long as I write down and use the data that was actually done, and that's what I did. So it's all going to be fine, and if that happens to you, just make sure you write it down and just don't ignore it, okay? So the amount of butanol, water, and acetic acid that are in the flask at this point in the video is the 30 milliliters that we had from all the 5 milliliter additions of water, plus 10 plus 5, so 45 milliliters of water. We still have the 20 mils of butanol, and now 10.12 is the amount of acetic acid that's in that flask. Okay, I'm going to add 10 more milliliters of water. Get your cloud up. Okay, I'm going to start to add acetic acid. Still cloudy. It's getting close. I might be there. No, not quite. It's getting close though. 2 drops I'm gonna add. Still looks cloudy on the side. It's very close. Actually, I think it's done. It's done. Reading 11.33. Another 10. Clouds right up. Add my acetic acid. Drip, 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 drip. Oh man, I think it's clearing up already. Not there yet. Almost. One drop. I think it went over. Oh, it's still a little cloudy. Getting close though. I keep saying getting close. What is actually going to happen? I think I did it. It's right there. I might have added a few too many drops there though. See this guy getting on. 12.40. More mils of water. Some continuous but quick dripping. There. Oh, that's clear. Probably went a little over there. All right. 13.48. Only 3 more portions to add. It's cloudy. Start adding acetic acid. There. One more drop. All right, there we go. This is 14. Something. 14.20. 10 more milliliters of water. Acetic acid being added. Add it a little bit. Clearing up, but not there quite yet. 1 or 2 more drops. It's 1, 2. Maybe he needs another one. Yeah, beautiful. That's 14. 14 point. 15.73. And now the last one. It's clouding up. Adding the acetic acid. I added 12 drops. Looks like it's almost there already. Another 5 drops. Not quite. 2 more. Clear. That is 15. Let's see. 15.12. And that is it for part 3. Thank goodness. And here's the data for part of part 3. So you could see that 20 milliliters of butanol was added, 5 milliliters of water, and then I record the initial volume on the burette as 0 and the final for this first addition of the water as 1.14. But I actually, added that acetic acid every time. I never took any acetic acid and dripped it anywhere but in the flask. So these final volumes here are really the total volumes at that point in the experiment. So while I put the final for the previous always as the initial for the next one, I didn't really even need to do that. And I kind of confused myself a couple of times, which you could see all the crossouts. I probably should have just had a running total of the final number of milliliters. And I just want to tell you something else about the lab, which is when you do this, what you use to figure out the compositions at every point are actually the total amount of the total volume of each of the components in the mixture at that time. So what you really care about is this final number here each time at each turbid point, because you want the total amount of acetic acid that's in there, not the amount that was added for that particular, to go from 2 to 3. You don't want that. You want what is the total amount of everything at this turbid point, at this turbid point, at this turbid point. So you'll have to use the total amount of butanol, which actually never changes. It's 20, plus all the water that has been added up to that point, and all the acetic acid that's been added up to that point. Now I want to point out the little mistake that I made. I explained this when I talked about the lab on the video, that for this number 8 here, I was supposed to add 10 milliliters. But in fact, I realized after I did it that I added 5. So I wrote myself a little note and put a star here. And then I went back and looked at the video and counted the number of seconds it took to transfer the milliliters. And I realized that this was 5 milliliters that was transferred. Another thing I notice here is that going from 7 to 8. So this was only went from 9.43 to 10.12, which is about half of going from 8 to 9.4. And so it didn't make sense that this was half the amount. This is also more than a milliliter. This is more than a milliliter. This is well under a milliliter. But the evidence that I used was the length of time that it took the water to flow for the 10 milliliter versus the 5 milliliter pipette. So I'm pretty sure about that correction. So this is only 5 mils added, and this is 10, 10, and 10 until the end. Okay, so those are all 10s there until the end. All right. Now we're up to the last part of the lab, part 4. And in this part, we find one tie line. This is a line that connects the point that represents the overall composition to the 2 points that represent the composition of each of the 2 phases when they separate. So what I have here is a sample where I have pipetted 25 milliliters of butanol and 25 milliliters of water. And for part 4, what I'm going to do is I'm going to take some glacial acetic acid, a small amount, just 3 milliliters. So I'm just going to put a little bit in here. And I'm going to pipette 3 milliliters of that glacial acetic acid into this flask with the butanol and water. Okay, so let me do that. Cloudy. I'm going to mix it up. So what I'm going to do is I'm going to mix it up, and then I'm going to separate the layers. Now, why would I do that? Well, what I want to do is I'm going to want to figure out what is the composition of each layer. Okay, so I'm not so interested in the overall composition. I want to know what's the composition in the upper layer and what's the composition in the lower layer. So I'm going to stir this for a while. Let me get that going. I'm going to do it in the hood because it's rather smelly. All right. It's probably not in the middle too well. Good and cloudy. It's definitely in the 2-phase region. Let it stir for a while. Let's see if the handout tells me how long to stir it. Add 3 milliliters acetic. Oh, 5 minutes. Okay, so I'll come back after 5 minutes. So now what I'm going to do is find the mass of the beakers that I'm going to put the lower and upper layers in. So I've zeroed out the balance, and this mass of the beaker that I'm going to put the lower layer in is 30.2054. So that's for the lower layer. Okay. I'm going to re-zero it. Okay. Mass of the beaker for the upper layer is 30.3402. Okay, so what I've got so far on this data, you could put it in a notebook if you were doing this in the lab. For the tie line, I've put 25 mils of water and 25 mils of butanol in 125 milliliter Erlenmeyer, and I pipetted 3 milliliters of acetic acid, and I'm mixing for 5 minutes, and that noise you hear in the background is the stir, so I'm still mixing. But in the meantime, I weighed these empty beakers that I'm going to put the lower layer and the upper layer in once I separate the layers. Alright, so my mixture here has been stirring for more than 5 minutes now. I'm just going to shut it off. And then I'm going to remove that stir bar because that's just going to get in our way. Try to get all the strips off of it. Just leave it on the hood. Okay, now, so here's my mixture, and it has the acetic acid in it. So what I'm gonna do, this, as you can see here, this is a separatory funnel. Okay, so I'm going to pour this into the set funnel, and then I'm going to separate the two layers. And I'm going to put the lower layer in the beaker for the lower layer, and then I'll weigh it, and the upper layer in the beaker for the upper layer. All right, how am I going to figure out the composition of each layer? Well, I can figure out the amount of acetic acid in the lower layer. I picked the water layer, right? That lower layer is mostly water. So what I'm going to do is I'm actually going to titrate that lower layer with sodium hydroxide to figure out the amount of acetic acid in it. All right, so right now I'm just going to pour. Let me see if I can set this up so I can have two hands. I'm sure I can. That. I think let's pour this in. This is straight good. Okay. So I'm just going to let it separate a little bit better. The white background's a little hard to see, but there you can see there's a line there now. Okay, so I'm just going to let it separate a little bit longer. Well, at least you can see the line now, the separation line. And, all right, let me get the lower layer beaker here. Okay. There goes the lower layer. It's coming out. Oh, I have to take this cap off here. Did it. That's the lower layer. Now I'm going to go and weigh it, mass it, whatever you want to call it. Back to the balance. So this is the mass of the lower layer with the lower layer in it. So this is the lower layer plus the beaker. 50.9421. Write that down. Now I'm going to go weigh the other layer. We'll have to get the other layer in a beaker first, so hold on. All right, now I've got that upper layer in a beaker, and it's 56.7127 grams. All right, and now I have to do a titration. All right, so what I'm doing is I'm titrating that lower layer. I poured the lower layer here into an Erlenmeyer flask. Then I thought I was filming the whole titration, but in fact the camera was on standby. So I have already added about 16 milliliters. And I was thinking out loud how embarrassing it would be to miss the endpoint. I really don't know if I'm that close, but maybe I'll put 2 drops. Yes, and then I just changed the battery, so that was great timing. Oops, I think I went over. Ah, not quite. Got lucky there. That took a while to go away. Oh, 2 drops. Okay. You could tell how much I want to go home. I've been here for hours. It's like 5:30. No, it's almost 6. Ooh, that was really close. I think I am done. That is a very faint pink. Not sure you could see it on the camera. Maybe I'll put another half a drop just to let you see it. Watch now, 3 drops will go in. I need a water bottle with a cover. Yeah, I really should have taken that reading before, but there, 1 extra drop. It's really bright. All right, whatever. When you do it, you should take the reading before you add the drop for the audience. Okay, so I'm reading this as 37 something. 37.60 milliliters. Okay. So going over here, I have my molarity of the NaOH there. I have my initial volume, which you missed because it was on standby, the final volume. And on the previous page, I have my volumes of both layers, and I'm done with this experiment. And this is the data for the last part, for the tie line. So this is the data for the tie line part of the lab, where I added the 25 mils of water and butanol into 125 milliliter Erlenmeyer, pipetted 3 mils of acetic acid, stirred for 5 minutes, and then I measured the volumes, I measured the masses of each of the layers, the bottom layer and the top layer, once I stopped stirring. And then I titrated the bottom, layer, and then I titrated the bottom layer with 1.046 molar sodium hydroxide, and these are the initial and final volumes. And I went 1 drop over the end point.